Welcome back, and in the last video we reviewed some kind of properties that give existence of an invertible matrix, and then also looked at how to find the inverse should we need to. But now we are going to look at some more properties related to invertibility. So here's a theorem that we're going to begin with, and we kind of mentioned this in the last video, but now we didn't ever really formally prove this. We just kind of said, oh, we noticed this, let's go ahead and prove it. So an n by n matrix is invertible if and only if the kernel of the matrix is a zero vector only. So proof, this is an if and only if, so we do need to prove two directions. Let's look at this direction first. So we're going to assume A is invertible. Okay, and we're going to let X be in the kernel of A. Okay, so then this gives us, so this means that AX is equal to the zero vector. And then, well, we can apply the inverse matrix on both sides. So then I'll just keep working across. A inverse AX is equal to A inverse of the zero vector. So then from all this, the left-hand side is just X vector. The right-hand side, if you apply the inverse to the zero matrix, or zero vector, you get the zero vector. So then that means that the kernel of A is the set that is only the zero vector. Boom, done. Okay. Now working the other way, we let, and that's the warning I kept on telling you about, so just ignore that. So let kernel of A be the zero vector. Okay, then that means that the nullity of A is 0, and the rank of A is n, because it's an n by n matrix. Okay, and consequently, this means that A is injective and surjective. Might need to reason through that on your own just a little bit, and or ask in class. And then consequently, since it's injective and surjective, that means A is invertible. Okay, so that's the proof, verifying that if we have invertibility for a matrix, that means that the kernel of the matrix is 0. Okay, and so consequently, there can't be a non-trivial linear combination of the column vectors for an invertible matrix, and then consequently the columns are linearly independent. Okay, some other statements that kind of fall in tow with this, if we have independent or linearly independent columns, then that means, and we saw this from the last video, that if we reduce row echelon form, look at the reduced row echelon form of A, we get IN. Okay, because there isn't any relationship among the columns. Okay, and then also we can say that A has linearly independent rows. We can look at either rows or columns here. Okay, so the big idea here is that invertible property means that the kernel of A is 0. We went through the proof. Again, if you have questions about why it is injective or surjective, be sure to ask in class, or again, maybe just reason through why this nullity and rank condition is sufficient for injective and surjective. And then if we have the kernel of 0, then that leads to non-trivial, or we can't have a non-trivial linear combination of column vectors, and then meaning columns are linearly independent. And then try and convince yourself why if we have linearly independent columns, we also have linearly independent rows. And so we'll pick up with more invertibility properties in the next video.